Okay, now moving on to section 7, where we're going to talk about how we transport these gases. If we're talking about oxygen, that's predominantly going to be transported by hemoglobin. And when we're talking about carbon dioxide, there's actually a couple of different ways in which we can transport carbon dioxide. So let's start with oxygen transport first. There's two ways in which oxygen can be transported. One way is bound to hemoglobin, more specifically the iron atom in each globulin chain within an erythrocyte itself. And the second way is just the gas dissolved in our blood plasma. But remember that oxygen is very poorly soluble in water, which is basically what our blood plasma is. So only about 1 to 2% of the oxygen being transported or carried in our blood is actually in the dissolved form. About 98 to 99% of all oxygen transport is going to be with oxygen bound to an iron atom in the actual hemoglobin molecule itself. And just as a reminder, I know we talked about this previously, but each hemoglobin molecule is made up of 4 globulin chains, 2 alpha and 2 beta. At the center of each of the globulin chains is an iron atom. And so oxygen is actually going to bind the iron atom in the center of each of these globulin chains. So each hemoglobin molecule can transport 4 molecular oxygens. Just a couple terms in regards to the level of oxygen bound to hemoglobin. If we have a lot of oxygen bound to hemoglobin, we then call the hemoglobin oxyhemoglobin. If we have if we're at our body tissues and we are beginning to drop off oxygen to the tissues themselves and we start unloading it, then we start saying that we have reduced hemoglobin or deoxyhemoglobin. So loading and unloading of oxygen is going to actually be facilitated by changing the shape of hemoglobin itself. As oxygen binds, once the first oxygen molecule binds to that first iron atom, that hemoglobin molecule is going to change shape. And it changes shape in a way that causes it to be more likely to bind more oxygen molecules there afterwards. So once that first oxygen molecule binds, it's going to readily uptake 2 more oxygen molecules, and even a fourth can be uptaken as well. If we only have 1, 2, or 3 oxygen molecules bound to a hemoglobin molecule, we say that the hemoglobin is partially saturated. If all 4 iron atoms in our hemoglobin molecule are bound to a molecular oxygen, then we say that the hemoglobin is fully saturated. The rate of loading and unloading of oxygen is regulated to ensure that we have enough oxygen being delivered to our cells themselves. So some things can influence how much oxygen we have bound to hemoglobin. One is going to be the partial pressure of oxygen, and the others are going to be factors like temperature, blood pH, partial pressure of carbon dioxide, and something called BPG. But all of these are correlated to each other, and they all are kind of the result of the exact same thing. So this is just an illustration showing you what happens to oxygen loading and unloading. For example, if we are to change our altitude, so someone at sea level versus someone at a high altitude where there's less oxygen, meaning there's a lower partial pressure of oxygen, again, the result of what's going on. This is kind of just showing you, again, just a big picture of something. Don't worry about the graphs or anything specific here. Okay, so let's first talk about the influence of the partial pressure of oxygen on hemoglobin saturation. The partial pressure of oxygen is going to be the predominant influencer of whether or not we're going to bind more oxygen or release oxygen. The percent of the hemoglobin saturation, it can be plotted. There is a graph in the image above. You don't have to read that. Just if you wanted to take a look at it, you're welcome to. The point is that the graph isn't linear, but it's actually S-shaped curve, and this is what we call the oxygen hemoglobin dissociation curve. And basically, it's not a fluid receival or release of oxygen, because again, we're changing the shape to change the affinity. In the arterial blood, the partial pressure of oxygen is about 100 millimeters of mercury and contains about 20 milliliters of oxygen per 100 milliliters of blood, so about 20% by volume. If we're talking about arterial blood, the hemoglobin is 98% saturated. So we're talking about the max amount that we have for oxygen saturation. Further increases in the partial pressure of oxygen, for example, if we start breathing very deeply, are going to produce minimal increases in the actual binding of oxygen to the hemoglobin. In venous blood, the partial pressure of oxygen is much lower. It's only about 40 millimeters of mercury and contains about 15% by volume. So our hemoglobin is about 75% saturated. So what the remainder of what's left after we drop off the oxygen to the tissues is what we refer to as the venous reserve. So that's the amount of oxygen still available in our venous blood that is still can be used. My point is with all of this is that arterial blood is our newly oxygenated blood that's coming from our lungs and going to be distributed to our body tissues. 98% saturation of our hemoglobin. Once we go and drop off this oxygen to our tissues, we are not completely depleting our hemoglobin of oxygen. We still have about a 75% saturation rate of our hemoglobin. So we never truly have completely unoxygenated or completely deoxygenated blood. We always have some level of oxygen bound to our hemoglobin, and that's what's referred to again as at venous reserve. So influence of other factors on hemoglobin saturation. So things like an increase in temperature or our blood pH, which is the same thing as our hydrogen ion concentration, or the partial pressure of carbon dioxide, or the amount of something called BPG in our blood, all can influence the hemoglobin saturation at any given partial pressure of oxygen. BPG is just 2,3-bisphosphoglycerate. It's a byproduct of the metabolism of glucose. And BPG can bind reversibly with hemoglobin, and its levels are going to rise when the oxygen levels are chronically low. So if we're talking about hemoglobin saturation, if we have a high hydrogen ion concentration, that would mean that we have a low blood pH or high acidity. If we have a high partial pressure of carbon dioxide or BPG, this is all indicated that we have gone through cellular respiration and used a ton of oxygen in the process, because all of these, an increase in temperature, an increase in the amount of hydrogen ion concentration, an increase in the amount of carbon dioxide we have, and an increase in BPG are all waste products or byproducts of cellular metabolism, meaning that we used a lot of oxygen, so we have low oxygen levels, and we have a high amount of these waste products. So if we have these high amounts of waste products, again, which are indicating that we consumed a lot of oxygen, what's going to happen is going to decrease hemoglobin's affinity for oxygen. Why? Because we want to decrease its affinity so we can actually unload more oxygen, because we're showing with high concentrations of these things that we use a lot of oxygen. This is going to occur in our systemic capillaries, and decreasing the affinity again is going to enhance the oxygen unloading, and it will shift the oxygen curve. If we have decreases in any of these factors, temperature, hydrogen ion concentration, the amount or partial pressure of carbon dioxide or BPG, we're going to have the reverse happen. We're going to decrease oxygen unloading from the blood, because we are showing that we have low levels of these, meaning we haven't used a lot of oxygen in these tissues. So these are just the curves showing you how different things can affect it. If we're looking at body temperature, what happens to the percent oxygen saturation of hemoglobin. If we look, if we increase our body temperature, say to 43 degrees Celsius, an increase in temperature is going to indicate that we're going to have less oxygen bound to our hemoglobin. So if we look at this curve, we have lower percent saturation of our hemoglobin. Why? Because an increase in temperature is an indication that we used a lot of oxygen during cellular metabolism and that we need more. So we don't want as much bound to hemoglobin. We want more of it being released from hemoglobin so they can enter our blood tissue or enter our body tissues. Same thing here. If we have any increases in the waste products like carbon dioxide or hydrogen ions or BPG, all of those would lower the saturation of hemoglobin because those are indications that we've used a lot of oxygen and that we need more to be unloaded from the blood. Okay, other influences or things that can affect hemoglobin saturation. Like I mentioned before, this is kind of repetitive, but BPG is produced during red blood cells during glycolysis. So that's the first stage in cellular respiration or the production of ATP. So because it's a byproduct of cellular respiration, which requires oxygen, we're going to have high levels of BPG when we have low oxygen levels. So as the cells metabolize glucose, they use the oxygen, again, causing an increase in all these waste products like carbon dioxide and hydrogen ions. However, when we have declining blood pH, which is the result of high hydrogen ion concentrations, it results in something called acidosis. And increasing the partial pressure of carbon dioxide actually is going to cause the weakening of the oxygen to hemoglobin bond, and that is going to be referred to as the Bohr effect. So oxygen unloading can occur where we need it the most. Heat production in active tissues is directly and indirectly decreases oxygen's affinity for hemoglobin as well. Again, also increasing oxygen unloading and getting it into our tissues where they need it. Okay, that was oxygen. Now we need to move on to carbon dioxide. And we have 3 different ways in which carbon dioxide can be transported. The first one is directly dissolved in plasma. A little bit higher of amounts are directly dissolved in plasma than that of oxygen, so about 7 to 10%. But this is still the smallest amount of carbon dioxide being transported this way. About 20% or a little over 20% of carbon dioxide can be found chemically bound to hemoglobin in the red blood cell as well. If we have carbon dioxide bound to the erythrocyte, bound to hemoglobin, then we refer to it as carbaminohemoglobin. One distinction between hemoglobin carrying carbon dioxide and hemoglobin carrying oxygen is that oxygen is bound to an iron atom in hemoglobin. Carbon dioxide isn't bound at the same place. It's not bound to an iron atom. Instead, it's bound to one of the amino acids in the globulin chain, which is why it's called carbaminohemoglobin. The third way that it can be transported is as bicarbonate ions in the plasma. So this is the bulk and the main way carbon dioxide is transported. So most carbon dioxide molecules, once they enter into your bloodstream and enter into your blood plasma, they will immediately go into your erythrocyte. And then there's some reactions that are going to occur inside your erythrocyte that are going to convert this carbon dioxide into a bicarbonate ion, which is HCO3 with a negative charge, so it's an anion. And that's how it's going to be transported inside of an erythrocyte. I'll show you an image of it in just a second. So again, we have carbon dioxide. Carbon dioxide is going to enter into the red blood cell where it's going to combine with water. It's going to form carbonic acid. Carbonic acid is incredibly unstable and is going to quickly dissociate into a hydrogen ion and a bicarbonate ion. So most of the carbon dioxide is actually transported in a different form, and that is as a bicarbonate ion. The process of converting it into a bicarbonate ion occurs in an erythrocyte. Why does it occur in an erythrocyte? Because that's the location of the enzyme needed to convert it into a bicarbonate ion, and that is carbonic anhydrase. So the enzyme responsible for catalyzing this reaction or conversion of carbon dioxide is inside the erythrocyte itself. So if we're talking about systemic capillaries, immediately after the bicarbonate ion is created, it's going to quickly diffuse out of the erythrocyte and back into the blood plasma. If we're talking about balancing of charges, we're losing a negative charge. We need to bring in a negative charge, and what's brought in as a bicarbonate leaves is actually a chloride ion. So a chloride ion comes in from the blood plasma at the same time as a bicarbonate ion is leaving the erythrocyte and entering into the blood plasma. This switch of bicarbonate ion and a chloride ion is referred to as a chloride shift. In the pulmonary capillaries, the processes occur, but they're going to happen in reverse. Once we have our blood reaching our lungs, we can't expire or get rid of a bicarbonate ion. We have to reconvert it back into carbon dioxide. So the bicarbonate ion in our pulmonary capillaries is going to go back into the erythrocyte, and a chloride ion is going to move back out into the blood plasma. Once we have our bicarbonate ion inside of our erythrocyte, it's going to combine with a hydrogen ion and form back carbonic acid. Carbonic acid is still readily unstable, so it's going to be split by carbonic anhydrase, at which point we're going to reform our carbon dioxide and water. And then carbon dioxide is then able to diffuse out of the alveoli so that we can actually breathe it out. So this is basically an illustration showing you what's happening. We can see right here, if we're talking about oxygen release and carbon dioxide pickup in the tissues, right here, we have carbon dioxide that's leaving our tissue cells to be picked up by our blood. So there's carbon dioxide. It's going to enter into the interstitial fluid and then eventually enter into our capillaries and eventually enter into our erythrocyte. As soon as it enters into the erythrocyte, it's going to combine with water very, very quickly and form the carbonic acid right there. Carbonic acid is very unstable and will quickly dissociate into a bicarbonate ion and a hydrogen ion. So we want the bicarbonate ion to go out into our blood plasma. So that's exactly what it does. It leaves and goes back out into our blood plasma. But because we're losing a negatively charged ion, we need to bring in a negatively charged ion. And we do. And that ion is chloride. So chloride ion comes in. The shift or the exchange of a bicarbonate ion for a chloride ion is referred to as the chloride shift. We also have a very small amount of carbon dioxide, again only about 20%, that will go in and bind to hemoglobin directly, not in the same place as the oxygen molecule, but instead will bind to an amine group on an amino acid, which is why once it's bound to hemoglobin, we call it carb-aminohemoglobin. Very, very small percent, less than 10% of carbon dioxide that's entering into our blood will just remain dissolved in plasma. This is showing you the reverse process that's happening once we hit our pulmonary capillaries. Once we hit our pulmonary capillaries and we actually need to get rid of the carbon dioxide and breathe it out, we have to reconvert the bicarbonate ion that we formed in our blood plasma erythrocyte back into carbon dioxide. So we still have a chloride shift. So again, we have our bicarbonate ion that's going to come in and enter into our erythrocyte. We have to balance our charges, so we lose the chloride ion that we originally brought in. Still referred to the chloride shift. They're just moving in opposite directions now. Once we have our bicarbonate ion back into our erythrocyte, there's an enzyme there that's going to turn it into carbonic acid, which is quickly going to dissociate into our original molecules, which were carbon dioxide and water. Carbon dioxide can then diffuse out into our interstitial fluid and eventually into our alveoli, so we can breathe it out. If we're talking about our carbaminohemoglobin, we're also going to be able to cause, we'll see why later, carbon dioxide will disassociate from the hemoglobin molecule because it's losing its affinity for it, and be able to diffuse out into our alveoli. And then the carbon dioxide that we had dissolved in our blood plasma can just directly diffuse out into the alveoli itself. So we have something called the Haldane effect. The amount of the carbon dioxide transported, like I mentioned previously, is going to be affected by the partial pressure of oxygen itself. The lower the partial pressure of oxygen means that the lower amount of saturation of our hemoglobin with oxygen that we have. The less oxygen we have bound to hemoglobin means the more carbon dioxide the hemoglobin can actually carry. And this effect is referred to as the Haldane effect. And that's going to reflect the greater ability of reduced hemoglobin to form the carbaminohemoglobin and to buffer the hydrogen ions by combining with it. So it might seem counterintuitive. Why do we bring in carbon dioxide, put it into an erythrocyte, and then convert it into a bicarbonate ion to send it out to the blood plasma to reconvert it back into carbon dioxide when we get it into the lungs to breathe it out? Well, the reason why is because the bicarbonate ion is part of the carbonic acid bicarbonate buffer system, which is incredibly important for our body. Our blood pH needs to be about 7.4 and has to maintain a very narrow range around that. So about 7.35 to 7.45. If we go outside of that pH range, bad things happen. So we have to have a buffer in our blood to make sure we can maintain that pH. And a buffer, just as a reminder, is something that can act as an acid or a base. So the bicarbonate ion that we just formed can act like a base, and then we have our carbonic acid, which acts like an acid. So turning it, carbon dioxide, into a bicarbonate ion is what helps create the buffer system for our blood so that it can help maintain that pH and resist any changes in pH. So if in the event that our hydrogen ion concentration in our blood rises, our bicarbonate ion that we formed will bind to the excess hydrogen ions and form carbonic acid, which is going to produce eventually carbon dioxide and water. In the event that our hydrogen ion concentration becomes too low, our carbonic acid can dissociate, releasing a hydrogen ion concentration, thereby elevating it back up to where it needs to be. We also have a respiratory rate that can kind of help with our blood pH. So in the event that we start to do some slow, shallow breathing, that's going to cause an increase in carbon dioxide in our blood, meaning we're retaining the carbon dioxide, we're producing carbon dioxide at a faster rate than we're breathing it out. Carbon dioxide is an acid. So if we're producing more of an acid than we're actually breathing out, that's going to increase the acidity of our fluid. An increase in the acidity means we've lowered the pH. The reverse is true if we decide to take rapid, deep breathing, so something like hyperventilation. We're breathing out more carbon dioxide or acid than we're producing. What's going to happen is that our blood pH is going to increase, thereby becoming more basic. So we can change our respiratory rate also to help with our blood pH, and we can also have that carbonic acid bicarbonate buffer system that can also help with our blood pH. So I'm not going to read these to you. That's why there is the little lightning bolt. But I kind of just want to point out that you need to kind of understand what the differences in these hypoxias are. So there's anemic, ischemic, histotoxic, hypozemic, and carbon monoxide poisoning that can also all contribute to an inadequate amount of oxygen being delivered to our tissues. So this is a good flashcard area or just basic definition, memorization of what the differences are between these hypoxias.